Well, thank you, Celia, for those very kind and wholly undeserved words. I'm a bit worried whether I can be heard at the back. Yes, apparently. Let me know if I fade away, okay, which I may well do. So I must first thank the members of the Society here assembled for the huge honour of inviting me to give this 46th Bartlett Lecture. The EPS has really provided me with a sort of scientific and professional family for most of my career. I well remember giving my first EPS talk in Cambridge. The fire alarm went off during the question period, thus saving me from answering a question by Tony Monsell. I'm sort of hoping the fire alarms will go off now, but I hope this won't be my last talk to the Society, but it's certainly the most terrifying given the distinguished roll call of Bartlett lecturers before me, some of whom are indeed in the audience. Secondly, I should like to acknowledge some collaborators. I'd like to name especially Robert Rogers and Nick Young, Celia just mentioned Robert, who as PhD students in Cambridge were my initial co-explorers in this domain. In Exeter, I must name and thank for organising today's symposium Aurelio Laverick, who's been my collaborator for the last 10 years. And jointly supervised with me PhD theses by Felice, Heike, Tobias, and missing one. Hi, did I mention? Are they all there? Who are we missing? Don't know. And also Ian McLaren, who I've my colleague Ian McLaren, who I've managed to tempt briefly into interest in cognitive control when we co-supervised Charlotte Forrest's PhD. I'll mention some of this work, but sadly not all. So, control of a task set. What is a task set? Let me try and explain it by just inducing one in your head. Okay? So I'm going to show you line drawings for several objects, one at a time. For each one, I want you, if you would indulge me, to decide how many syllables the name of the object has in English and raise the corresponding number of fingers on your right hand as quickly as you can. For example, this is an arrow. It has 2 syllables, so you would raise 2 fingers. Okay? Right, ready? Off we go. Okay, this was a bit unfair on the non-native speakers, but you seemed mostly, however, to manage that all right. But how? So somehow you cobbled together a novel processing architecture out of some of the components you already have in your head, and you got it to work. You oriented your visual attention to the screen, you got your fingers ready, you activated the link between visual object recognition and name retrieval, all of which you've done many times before. You fed each name into your phonological buffer and applied to it a syllable counting routine, which again you've used before. And then you translated the number representation obtained into a manual gesture according to the little rule I gave you. And after only a little practice, or perhaps even before, as we have heard earlier this afternoon, you could set yourself so that when the next picture appeared, this whole sequence of processes ran off at high speed, and up went your finger, what Exner called a prepared reflex. Isn't that magical? So, to be a bit more formal, what's a task set? It's a subset of the processes and representations available in your mind and brain that have to be appropriately organized, linked, and tuned so as to orient attention appropriately with respect to modality, object, and attributes, activate appropriate effectors, so you've got to get speech versus reach and touch perhaps ready, if overt action is required for the task. You've got to instantiate appropriate input-output translation rules or procedures. You've got to adopt suitable decision and response criteria, and all in such a way as to accomplish the goal of performing a specific cognitive task when the appropriate input is available. Now, in life, of course, we acquire task sets of varying complexity through trial and error, through observation of others, and sometimes from explicit instructions. I'm going to focus on relatively simple and discrete input-output tasks, the sort of tasks that we can measure reaction times of in the lab, and errors, that are required from instruction, and there'll be plenty of examples later. Now, of course, many of you have put participants through the acquisition of simple tasks like these, which you designed to exercise some process of interest, like word or face recognition, or mental rotation, or visual search, or whatever. You generally gave a bit of practice so that performance became fluent and so on before collecting data. And when performance has become fluent and stable, you can bring the participant back after an hour or so, or even a day or so, and ask them to do the same task. And without further instructions, they rapidly get their mind and body organized again, retrieving this once novel task set as a procedural package from memory and executing it fluently when you present a stimulus. At the other end, so that's the initial acquisition with a little practice, but we can look at the other end of the life history of a task set. So we can study skills like word reading that life has practiced for many thousands of hours, or we can give heroic participants many thousands of trials on an initially novel task until it becomes habitual, or with suitable scare quotes, automatic. Okay. Now here's, just as a random example, some data from one participant performing a dot counting task for 12,000 trials. Performance obviously not my data, I wouldn't do this. Performance obviously goes on improving for a long time, though with diminishing returns. And some of the improvement may reflect the discovery of a more efficient strategy, for example, shifting from rule-based responding to instance-based responding, and some undoubtedly reflects incremental associative learning of the various links required for whatever strategy is being used. Now, there's nothing at all new about this characterization of the life history of task set. William James is still worth reading on habit in chapter 5, I think it is. Fitz and Posner identified 3 similar stages in the acquisition of complex motor skills: cognitive, associative, and autonomous stages. And we heard Kai Longman earlier on mentioning Chine and Schneider's learning of cognitive skills review paper, where they talk about task formation, controlled execution, and automatic execution. Frederic Bartlett, who I'm obliged, of course, to mention, in his book Thinking, suggested that we should take what he called bodily skills as the model, or the acquisition of bodily skills, as the model for the development of thinking skills. But he was, I'm afraid, very skeptical about the possibility of learning anything useful about skill by looking at the sort of simple input-output reaction time tasks that I'm going to be talking about. Now, apart from enabling my ritual genuflection to Sir Frederic, after whom these lectures are named, consideration of this life history of a task set is important, because the nature of the control of task set changes through this life history. So at the beginning, the instructions, the rules of the task, and what the stimuli will be like are presumably represented in declarative working memory. But then somehow during, or even before, the first few performances of the task, a compiled and effective procedure is created in a different memory system, procedural memory, from which it can then be retrieved or activated at will. And this compiled procedure then becomes optimized through repeated exercise and feedback. At the beginning, the main issue is how control is transferred from a declarative representation of instructions to a compiled representation in procedural memory. And once this has happened, the control question becomes, how do we re-enable that task set voluntarily or endogenously from procedural memory when it's required? And as task sets become more habitual or automatic, the question shifts to how we cope with inappropriate task sets becoming activated exogenously by stimuli which afford the task. And I think it's a slight caricature, but it's true to say that the psychology and neuroscience of task set control have been working their way backwards through these questions over the last 60 years or so. So I'm thinking, of course, initially of Tim Challice's account with Don Norman of executive control, prompted by phenomena such as perseveration or utilization behavior in patients with damage to prefrontal cortex, Stroop and related paradigms where we attribute interference to the involuntary tendency to perform a practice task, like reading a word, and questions of everyday control. How do we resist the temptation to eat another biscuit, drink another glass of wine, whatever it is? In the 1990s, as Celia has mentioned, saw the development of task switching paradigms, which is really what I'm going to be talking about, for the control of looking at the control of null but fluent task sets. Usually tasks we're just given the subject to learn with a bit of practice, and then we collect data for a session or 2 or 3. And it's only in the last decade or so that a body of research has developed around the mysterious transition from instruction to fluent performance during initial acquisition of a task set. And I don't know much about this, so it seemed a very good idea for the symposium preceding this lecture to bring together some of those who have been doing this research, this initial acquisition stage. And this afternoon we did indeed hear some fascinating findings and ideas from experiments that look at performance and brain activity during or even before the first few performances of a task. My own work on task set control has been mainly on what happens next. Once a task set has been acquired and compiled into procedural memory, how does that procedure get enabled and disabled? So that at one moment it's determining how sensory information gets translated into action, and the next moment it's not. In the early 1990s, I went to an EPS dinner and sat next to Vicky Bruce. And as the evening wore on and I became more biddable, she persuaded me to write a chapter for a book she was editing called Unsolved Mysteries of the Mind, targeted mainly at students. And my unsolved mystery was to be control of mental processes. Here's how I introduced the mystery. We can, for many cognitive skills, say something useful about what the component processes are, how they work and how they're organized. What we're unable to say much about is how that particular organization, rather than some other, is called into play at a given moment. To address this question experimentally, you've got to call task sets into play. And that means you've got to get people to switch back and forth between tasks. Now, there'd been some research on alternation between tasks going back to Jersild in the 1920s, and a few isolated papers on task queuing by Henry Schaffer, Irv Biederman and others. But in the 1990s, several labs independently, mine, Alan Orport's, Nachshon Mehren, Danny Gopher, and then Ulrich Meyer with Kiel in Oregon, independently developed better ways of doing such experiments and discovered some interesting phenomena. And then we all found out about each other, and the research area called task switching sort of took off. And we began to get sessions at Psychonomic Society called task switching. Okay. So these experiments all basically involve, or at least almost all of them involve, task queuing. What do I mean? So they induce the need to re-enable a task set frequently by presenting on each trial a stimulus that affords one or more of a small repertoire of pre-trained tasks. You queue the task to perform on each trial, and the task sometimes repeats and sometimes it changes, either predictably or unpredictably. It depends on the paradigm. And we examine modifications or modulations of performance or brain activity on task switch versus task repeat trials, all other things being equal. That's a very important proviso. When the required task differs from the task the performance performed on the previous trial, presumably some act of control is required to enable the required task set and disable the previous one. And that exercise of task set control is what we hope to capture and manipulate. So let me get concrete now and show you a specific example. So here the stimulus on each trial was an object name, a word like mountain or ant. At the beginning of the session, we practiced participants separately on two tasks to get them to the point where they were fluently performing these tasks. They either had to classify the word as having one or two syllables or as referring to a big or small object. Okay. And for the rest of the session, a cue was presented before each stimulus to tell the participant which of these two tasks to perform. In this experiment, the cues were visual icons like this. So either of those two cues meant to do the syllables task. Either of those two cues meant to do the size task, because the criterion was bigger or smaller than a football. And so each trial basically went like this. The cue appeared, and the participant then saw the stimulus and had to make a response. There are two manipulations of importance here. So the stimulus word changed on every trial, but the cue could stay the same or change, and the task could stay the same or change. So there are three possible transitions, which you can see down at the bottom here. So that's an example, for instance, where the cue changes and the task changes, but the cue could change and say that it's to indicate the same task again, or both the cue and the task could repeat. And the other thing we varied was the interval between the cue and the stimulus to vary the amount of time the subject had actively to prepare. And notice that we've kept the interval here constant, so the time since the previous performance is constant. What we're manipulating is opportunity for active preparation. So on the left here we have reaction times as a function of Q stimulus interval, and you can see obviously that it's much easier to do the task when you've had a bit of time to prepare, but what we're interested in is the difference among these functions. And so these are plotted over on the right. So the black line here is the task switch cost, the difference between task switch and task repeat, and the Q is changing in both cases. Okay. And you can see that if there's no time to prepare, there's a very substantial switch cost. As the subject's given more time to prepare, this reduces, but it doesn't disappear. It seems to reach a non-zero asymptote. These are the phenomena I'm going to focus on: switch cost, its reduction with preparation, and the non-zero asymptotic cost. But let me first mention a couple of methodological precautions we have to worry about. So the grey line here represents the effect of immediately repeating a Q when the task stays the same. Okay. And you can see that there is what you might call a Q priming effect. If you've just encoded a Q and you now get the same Q again, you have an advantage. And that tells us one precaution we have to take. If we used only one Q per task, as many early task queuing experiments did, we wouldn't be able to unconfound the effects of a task switch from these effects of Q priming. So we always have two Qs per task, and we never repeat the same task immediately. We've also found that we need to keep the probability of a task switch relatively low. So if we manipulate the probability of a task switch, we and others have found that it often affects switch costs in a way that suggests that if you switch tasks half the time, then the subject begins to prepare for a task switch even before they've got the Q. And we don't want them to do that. We want them to start preparing for a task change only when they've been queued to do so. So we usually keep the probability of a task switch at something like 1 in 3. So the participant expects the task to repeat unless the Q tells them to do otherwise. So let's now focus on this pattern of switch costs, which are a few examples are seen up here. You'll see many experiments in which we have measured not the whole function, but 2 or 3 points on the function later. So basically, as more time is available for preparation, up to somewhere between 1/2 and 3/4 of a second, there is a reduction in switch cost. And we use the acronym RISC to describe this effect, the RISC effect. But the switch cost is not eliminated by preparation, no matter how much time we allow. There's an asymptotic cost, often called the residual cost, the cost that's left when you've done all the preparing you can. And there are studies in the literature with preparation intervals of 3, 5, or even 12 seconds, where you still get a residual switch cost. So this residual cost appears to indicate a limit in our ability to completely prepare for a change of task. It seems you have to perform the task at least once, and as Koch et al. Have actually shown, you have to emit a response to overcome this residual cost. That we can reduce the cost of a task switch by active preparation suggests that at least some of the enabling and inhibiting some of the enabling of the new task set and perhaps active inhibition of the previous one can be done before the stimulus appears. Rogers and I call this enabling and inhibiting task set reconfiguration. Now notice I'm not denying that participants actively prepare to do the task on task repeat trials as well. I'm sure they do. But when the task repeats, such preparation merely maintains or reinforces the existing configuration. It doesn't reconfigure the task set. So the active control may be the same, but the consequences in terms of impact on the organization and parameterization of processing is very different on switch and repeat trials. If on a task switch trial you don't have time to reconfigure a task set before the stimulus appears, then this control activity has to be done before the stimulus appears. Then this control activity has to be done during the latent interval after the stimulus. And this might slow task-specific processing in at least 3 ways, which are not mutually exclusive. So doing task set reconfiguration at the same time might insert some extra processing stages after the stimulus has appeared. It might share resources with task-specific processing, or it may simply be that task-specific processing is just less efficient until it's been fully reconfigured. I feel duty-bound to mention that this task set refiguration account of the RISC effect has been challenged. In particular, Gordon Logan and Klaus Bunderson and Daryl Schneider have argued that in a task queuing experiments, participants don't actually switch tasks at all. they perform just the single task of retrieving the response appropriate to the combination of cue plus stimulus. Okay. In fact, John Duncan used to say something very similar when I started to talk about this stuff in Cambridge. He'd say, there is only one task, Stephen, and that is life. So where do the switch costs and the RISC effect come from? These authors think that they can be explained by the cue priming effect I showed you. So they claim that cue encoding is facilitated of the same cue, or they claim a cue with the same meaning occurred on the previous trial. Now, I won't explain this account in detail because I think it's now clear it just doesn't work. So just three fragments of evidence. We've done experiments where we actually push with very small sets of stimuli. It becomes plausible that subjects would learn stimulus plus cue response associations. Okay? So we actually push subjects to do that. And they can. And when they do, though, the pattern of performance we get is very different to what we get when we give them the standard sort of task queuing instructions. Uli Meyer showed us this afternoon some very nice data using decoding of EEG such that he could show that rule-related activity, task rule-related activity during the cue stimulus interval predicted RT, but cue-related activity did not. And finally, Kate Arrington did a very nice experiment where she showed that if you actually delay the stimulus onset until the subject has indicated that they have encoded the cue, okay, you still get big task switch costs, so it can't be that the switch cost is due to cue encoding. Okay, duty done. I'm now going to go on assuming that the slope and asymptote of the RISC effect do in fact index the speed and efficacy of an anticipatory task set reconfiguration process. We can therefore use it to explore properties of task set reconfiguration. Let me give you a couple of examples. One conception of task set reconfiguration manifest in, for example, Klaus Oberauer's 2009 model of working memory is that it involves retrieving one of the task sets currently active in long-term procedural memory into a procedural buffer in working memory. A general property of memory retrieval, all over the place, is that it gets harder the larger the set of candidates from which retrieval is required. So we might expect task set retrieval to get harder when there are more task sets in play. To see if this was so, Felice van 't Voet devised sets of stimuli with 5 attributes that each afforded each of these attributes afforded an orthogonal binary classification. These objects were pictured objects in one case, they were words in another experiment. Now, if you simply queue one of 3 tasks randomly, the task you're queuing will on average have been more recently and frequently exercised than if you queue one of 5 tasks randomly. So we controlled for frequency and recency. And when we did that, we got a very respectable RISC effect. The task switch cost is reducing by about half as the interval gets longer. But there is absolutely no difference between the data for switching among 5 tasks and switching among 3 tasks. Okay, the reason you can only see 2 lines there is that the data for the 3 and 5 alternatives are simply sitting on top of each other. So the difficulty of re-enabling a task set doesn't seem to depend on the number of task sets in play, and our models are going to need to accommodate that. Another rather fundamental question about task set reconfiguration is whether it's a discrete or a continuous process. So if you do think of task set reconfiguration as promoting one of the active task sets into a procedural buffer in working memory, that seems like a discrete process. The task set is either in or isn't in working memory. In contrast, connectionist models of task set reconfiguration tend to model top-down control as an incremental shift in bias through a continuum. Let me make that a bit more concrete by taking a brief look at Sam Gilbert and Tim Challis's connectionist account of switching between word naming and colour naming of Stroop stimuli, and a model that's recently been elaborated locally by Sexton and Cooper. The word naming and colour naming pathways, that's the word naming pathway, that's the colour naming pathway or network, they're implemented by separate input-output networks. The output units in each pathway also receive activation from task demand units up here, mutually inhibitory task demand units, so as to favour the output units of the relevant pathway. On a switch trial, the top-down input shifts the bias incrementally or gradually from one to the other pathway. So a longer preparation time achieves a stronger bias before the stimulus onset, and that explains the RISC effect. Now, Ritzke de Jong proposed that the preparation underlying the RISC effect is not incremental, but all or none. The residual cost then results from a mixture of trials on which preparation is complete and trials on which this discrete advanced reconfiguration process fails. And somewhat to my surprise initially, when I did it, when I tried this test, it has been found that with an additional assumption or two, reaction time distributions on the prepared switch trials can be quite well modelled by a mixture of trials from the reaction time distributions from unprepared switch trials and from prepared repeat trials, which is consistent with advanced task set reconfiguration being a discrete process that sometimes fails. However, as you mostly all know, it's always hard to discriminate a discrete transition between cognitive states from a continuum if we have to average over many trials. And that's especially true if the task set bias achieved by the continuous transition is highly variable in its effect from trial to trial. One place we see this variability is in an electrophysiological signature, or what we believe to be an electrophysiological signature of task set preparation called the switch-related positivity. So let me illustrate. Stimulus was an outlined coloured shape, which I'll show you an example of in a minute. The tasks were to identify the shape or the colour with one of 4 key presses. The tasks were cued by the words colour or shape or one of these 2 icons. So a trial essentially went like that. You saw the cue and then the outline coloured shape surrounded it. And that was after a short or long preparation interval. Queuing at the longer intervals substantially reduced the switch cost. That's what's shown there. The switch cost gets smaller. So clearly preparation was effective on at least on average. So now we look for brain correlates of preparation during the longer CSI. Okay. And this is what you want to look up here. These are ERP waveforms for one electrode about here. But they illustrate that, as you can see, halfway through the preparation interval, this is before the stimulus here, halfway through the preparation interval, we see an extra positivity on switch trials compared to task repeat trials. Here's a temporal PCA analysis in which a single component reflecting this emerges with this sort of scalp distribution. But does this have anything to do with behaviour? Well, effective preparation presumably leads to faster responses. So we partitioned the switch and repeat trials separately into those with fast, medium and slow responses, and we looked at the ERPs for these subsets of trials. And you can see that for trials with fast responses, there's a substantial separation between the switch and repeat trials, a big positivity, and whereas for the slow responses it's very hard to detect any such effect. And Karianidis and colleagues in Australia, in a more elegant and fine-grained analysis, have confirmed this rather more elegantly. That is, it confirmed the pattern that the amplitude of the positivity decreases for switch trials with longer response times. So preparation for a change of task is highly variable from trial to trial, but not necessarily all or none. And models of TSR need to accommodate this. But relatively abrupt and variable changes in state are not necessarily incompatible with connectionist networks. Some have a gating process that allows relatively abrupt updating in response to control input. Another way in which voluntary top-down control of task set seems to vary in degree can be seen if we look at a run of trials following a task switch. Here the stimulus was a digit and the tasks were classified as odd, even or high, low. The cue was the colour or shape of the background and changed immediately after the previous response. And we varied the time available for preparation before the digit appeared. Now what's shown here is performance over a run of 4 trials in which the task stayed the same after a switch. So that's the switch trial number 1, and here's repeat, repeat, repeat. Okay. There's the switch cost, and you can see that it reduces with preparation to an asymptote. But what I'm interested in here is the position of run effects. These are subjects who switch tasks every 4 trials, and they know this. So it's completely predictable. And you can see that the switch cost is gone immediately. Okay, they're back to baseline. Here's a group of subjects for whom the task is unpredictable. It switches 1 in 4 trials, but randomly. Okay. And though the physical manipulation here is identical, you can see that now it takes much longer to return to baseline. It's as if the subject is sort of holding back on committing themselves to an extreme task set bias because they might have to switch back again at any moment. But doing the task 3 more times gets them down to baseline, essentially, even though they may have to switch back immediately. So we've got an interaction between endogenous control and exogenous control. So let's take stock briefly. If I have a sip of water to do so. So the RISC effect and its electrophysiological correlates suggest an endogenous task set reconfiguration process that's not dependent on the number of tasks in play, but is highly variable in its efficacy. Position in run effects suggests that when a switch of tasks is required, participants may modulate the top-down bias they apply as a function of their expectation of when another task set may occur. Now I want to sort of change the question a bit. On what, or on top of what, or into what system is this act of control applied? Okay. So it seems to be modulating some sort of competition between the task sets in play, but what's the nature of that competition? A place to start is the effect of response congruence. So here's the experiment I just showed you, in which, like many other such experiments, we use the same set of responses for the 2 tasks. Okay. And one thing we always find is that the reaction times are longer for stimuli like this one, for instance, which have different responses in the 2 tasks than stimuli to which the same response is made in the same task. You press left to both these. Okay. So that response conflict effect or congruence effect is showing us that the other task's SR mapping must still be active, and it's either helping if the 2 responses are congruent, or it's hurting if the responses are incongruent. And I hope that this effect reminds you of many other response conflict phenomena, and in particular you might think of the Stroop effect, the interference you get with colour naming when the word is a word in conflicting colour. And the standard interpretation of this is that stimulus involuntarily activates the familiar response of pronouncing the word, and this competes with the colour naming response if it's incongruent, or facilitates that response if it's competes if it's incongruent, facilitates if it's congruent, relative to a neutral stimulus which is not associated with a reading response. In task switching, however, we see a different pattern, and that's why I was stressing response just now. Okay, so here's an example. Stimuli are not colours here, but they're coloured words, but they're arrows with direction words in, and the subject must respond left or right, either to the arrow or to the word. Okay, and we also have neutral stimuli which only afford one of those tasks. And you can see that the pattern is different from what I just showed you. We're getting the standard congruence effect in the sense that incongruent are slower than congruent responses, but the responses are faster still when we have stimuli which don't afford the other task. Okay. So the benefit of response congruence here is being overridden by the cost of competition between task sets. It's possible also to detect competition without task set competition without response competition, even if you're doing colour naming without switching under some circumstances. So Kinoshita, DeWitt and Norris have recently confirmed an observation we made some time ago, where both sets of experiments got subjects to colour name character strings like familiar words, pronounceable non-words, matched in all sorts of ways, consonant strings, and these control symbol strings. Okay. And unusually for a Stroop experiment, each stimulus occurred only once. And under these conditions, here's the pattern of reaction times we got. Okay. So reaction times were actually roughly equal for the words and the pronounceable non-words. Now, if this was response competition, then you would expect the interference to depend on stimulus-response associative strength. And it just doesn't, because clearly non-words don't have any associative strength, and words clearly do. So it's got to be something else, and it looks as if it's the pronounceability of the stimulus that's determining whether you get interference or not. So if the stimulus is pronounceable, that evokes the task set of pronouncing, at least under the conditions where you are supposed to be pronouncing stuff. Okay. Returning to the task switching situation, the picture I'm trying to establish is that task sets, not just responses, compete to determine processing, that top-down control processes modulate or bias that competition so that the appropriate task gets performed, that the RISC effect indexes endogenous preparatory biasing of the competition if time allows, and that the residual cost reflects a limit on what endogenous advanced preparation can achieve, or maybe chooses to achieve in some cases, in biasing this competition. And if the words bias and competition remind you of the Desimone and Duncan biased competition account of visual attention, that's fine by me, okay? Though the competition is between task sets, not visual objects. And it seems clear that the task set competition is not just response competition or response conflict. Well, what could that mean? It could mean that more abstract or higher level representations of the task are competing directly, as in the inhibitory links between task demand units in the Chalice and Gilbert model. Or it could mean that some other component of the task set other than SR mappings compete, and I'm going to provide you some evidence of that in a minute too. First, let's consider how the competition is maintained. The term task set inertia, coined by Alan Allport, captures the idea that task set state, activation of one task set and inhibition of its rivals, simply persists or carries over from one task to the next, one trial to the next. So if you've just done task A and thus inhibited task B, and now have to switch to task B, you've got to overcome the inhibition of task B and enable it in the face of competition from persisting activation of task A. Okay. Applying endogenous control, for some reason we don't understand, does not fully overcome any carryover of task set state from the previous trial. The residual cost reflects what's left. The other idea, also due to Alan Allport with a different group of colleagues, is that task sets become associated with specific stimuli or categories of stimuli, and competition arises or is enhanced when the stimulus retrieves a competing task set previously associated with the same stimulus. The first of these is essentially short-term priming of task set. The second is associative reactivation of task set from long-term associations. The most direct evidence from inertia comes from an fMRI study by Nick Young and colleagues at Princeton. So they presented a face and a superimposed word on each trial. Participants performed a series of 4 trial mini-blocks. Each mini-block was preceded by a cue to classify the 4 words by number of syllables or the 4 words by gender. And the task either changed between mini-blocks or not. And reaction time was longer on the first trial of a mini-block when the task changed than when it didn't. That's the task switch cost here. In another part of the session, they localized brain regions which were selectively activated by doing the face task versus doing the word task. And then in the switching blocks, the size of the reaction time cost was correlated with brain activation associated with the competing task, the other task. So the cost of switching to the word task correlated with activation of the right fusiform face area, and the cost of switching to the face task correlated with activation of a region selectively activated by the word classification task in left inferotemporal gyrus. More indirect evidence for task set inertia comes from a paradoxical pattern of switch costs seen when you have to switch between 2 tasks very different in their familiarity or degree of practice. So once again, here are the Stroop word color naming and word naming tasks, slightly differently arranged here because you have to name the color of the background or the color of the word. The black lines here are reaction times for these incongruent stimuli. Here's the word naming times. You can see word naming is much easier than color naming. That's the dominance relationship we expect. But what is unexpected is perhaps that the cost of switching to the word naming task is higher than the cost of switching to the color naming task. And that's the paradox. Why should it be harder to switch to the easier task? Well, Allport proposed that you have to inhibit the dominant task more to perform the subordinate task. Undoing this persistent inhibition on the next trial was what's amplified the cost of switching to word naming. Nick Young and I developed a little mathematical model in which we assumed that task set activation simply carried over from the previous trial, and then response activation was a nonlinear function of this task set priming, of relative task set strength, and the application of just enough top-down control to get the right task done, or bias to get the right task done. And though I'm not going to show you this task captured nicely the model captured nicely this pattern, and also captured another finding we made, which is if we delayed the word a little bit, that reversed the asymmetry. And the model did that too. Evidence from the other idea that competition comes from stimuli reactivating task sets comes from manipulations of the history of individual stimuli. So Vacak and colleagues had participants name either the word or picture in stimuli like this. And they found that the word naming was slower, at least on switch trials, when the picture had previously been named. So they argued that stimuli must be evoking task sets with which they've been associated, and that this amplifies competition on switch trials, which here is contributing substantially to the switch cost. And this happens over long lags, so this must be like 100 trials even, must be long-term memory, not short-term memory. And moreover, it happens even for stimuli which have the same name for the picture and the word. So it cannot be competition, cannot be stimulus-response associations, must be stimulus-task associations. Here's a rather simpler manipulation of associative history. So we had subjects responding to words or names. Their tasks were either to classify the number of syllables or whether it was a word or name. And each stimulus occurred twice in the whole experiment, with a lag of somewhere between 5 and 37 trials, with the same task queued or different tasks queued on each encounter. The data are actually terribly straightforward. When the stimulus had been seen in a different task a few trials ago, reaction time is about 50 milliseconds longer, a little bit slightly smaller when you've had time to prepare. Oh, and again, I want to say this was true for response congruent stimuli, so this is stimulus task, not stimulus response binding. So clearly, stimulus-task association here is modulating the task competition, but with this particular task pair, there's no interaction with switch and repeat, so it's not actually causing the switch cost. So to sum up, competition is maintained by both reactivation of competing task sets by stimulus-task set association and task set inertia. The first is supported by the effect of prior stimulus-task associations over long lags, but this is not always the source of the switch cost. Task set inertia is supported by the fMRI evidence I mentioned, and then can also provide an account of this paradoxical asymmetry of switch costs and its reversal. However, since Ulrich Meyer is sitting right in front of me, I am obliged to mention that this asymmetry can also be seen under conditions where task set inertia, where transient inertia cannot be the cause. They had subjects performing the dominant and subordinate tasks in separate blocks of trials, and then there was either just a brief interruption, a 5-second pause, or in different experiments they had to perform a third irrelevant task like arithmetic. When they then had to resume performance, there was a restart cost, and that restart cost showed the asymmetry that I've mentioned before. Okay? And there can't now be transient task set inertia from the competing tasks. You haven't done it for a long time. I'm not going to explain that. Last issue I want to address. Back to the question of what it is that competes. I've tended to talk as if task sets are sort of unitary entities which get enabled, disabled, and engage in competition. Yet I did say at the outset that a task set is a complex. It's a complex of attentional parameters, of activating appropriate effectors, of instantiating particular SR rules, and adjusting criteria, and no doubt other things you could put on that list. Okay. The residual cost shows us that at least part of that complex isn't fully reconfigured or re-optimized until the task has actually been performed once, or sometimes more. So the question then is, well, which parts are not fully reconfigured? To make this a bit more concrete, suppose the stimulus you're going to see on each trial looks like that, these rather strange words with letters coloured in them. And suppose your task is semantic classification. Well, to do that task, you're going to have to do some orthographic encoding. You're then going to have to find a match in lexical memory, retrieve the appropriate semantic attributes, categorize them, select the appropriate abstract response, and then convert that into muscle twitches. Now suppose you have to switch to that task from another for the same stimuli that requires you to classify the symmetry with which these colours are distributed over letters, which is a much easier task than it might sound. Okay. So now you're going to do something different. You're going to have to attend somehow to the colour and their locations, and so there's some perceptual encoding of going on here. You have to do some sort of symmetry computation, and then you select a response and execute the response. Now, supposing you're switching between this task and this task, and incidentally, we chose this task because these two tasks because they require roughly the same distribution of spatial attention over the character string. Okay. Supposing you're now switching back to this task, we know we're going to get a switch cost, at least we think we do. Which of these processes is prolonged by having to switch? Is it response selection? As I've said, we've often tended to assume, I think largely because of the occurrence of response congruence effects, that the real problem with switching tasks, the big problem is the conflict between the two different stimulus-response mappings. Okay. How are we going to find out whether that's true? What would be nice if we could find an ERP marker of particular processing stages. And we know that word frequency influences lexical access, has a big effect. And we also know that effects of frequency emerge in the ERP at around 150 to 300 milliseconds. So if we now look at the emergence of the frequency effect on switch versus repeat trials, if we find a delayed onset of the frequency effect through having to switch, that would imply that a process earlier than response selection has been prolonged. So we did the experiment. So subjects saw one of these coloured words. There are a large number of words in this experiment, so they're seeing a new stimulus on each trial essentially, and they are queued in the usual way, 2 queues per task, and they are classifying either the animacy or symmetry. The reaction time switch cost we get with this 800 millisecond preparation interval is about 50 milliseconds, and in another experiment we show that it's much longer if you reduce the preparation time, so we think this 50 milliseconds is the residual RT switch cost. And what I'm showing you here is, I've leapt straight to difference waves. Okay, so what I'm showing you here, if I can make sure I tell you correctly what I'm showing you here, is the difference in global field power, that's an average over electrodes, between the ERPs for low and high frequency words. And you can see that an effect of frequency begins to emerge around about 250 milliseconds into the latent interval. Okay. But then the evolution of that frequency effect appears to be somewhat delayed for the black line here, which are the switch trials. Okay. For instance, that minimum there seems to be delayed by about 44 milliseconds, and that's a significant delay. I won't tell you how we work that out. So about 350 milliseconds into that delay, we're getting a frequency effect delayed substantially relative to the reaction time cost of 50 milliseconds. Another similar experiment where we switch between lexical decision and symmetry. Okay, the difference wave for the effect of word non-word here is what you're seeing, and I hope what you can see is that there's clearly a little delay here in the onset of that effect on the switch trials, the red data here. So 200 milliseconds into that reaction time, switching from the symmetry task is delaying the onset of the word non-word effect by 59 milliseconds, which just happens to be eerily identical to the reaction time cost. Now, of course, there are big standard errors around. Those are the standard errors around those numbers. So at least a substantial fraction of the residual reaction time cost here is due to a slowing of early processes. Well, what can that mean? We think it probably means that that the subjects have incompletely retuned their stimulus set or attention to encoding orthography versus the colour pattern. Okay, so we've got here an incomplete reconfiguration of the attentional parameters of task set. Now those are quite complex properties, orthography versus symmetry of colours and so on. Here's a rather simpler case of the same thing. Here the subject saw a coloured letter. They had to classify it as having a warm or cold colour or as a consonant or vowel. And they got auditory cues, and the interval here is about 1,000 milliseconds. And we also manipulated here the frequency with which particular colours occurred. So the central colours here occurred 8 times as often as the other colours. That manipulation delays the difference wave here for frequent versus infrequent colours. Okay? That's the blue versus the green here, and that delay, our best estimate of it is at about 17 milliseconds, a significant 17 milliseconds, and that's relative to the residual RT switch cost here of about 45. But notice this is really early. Okay? So it's entirely plausible that what is happening here is that a colour is just being processed more slowly if you've just been attending to shape. So that shows you some evidence for what we've come to call, though I think that this might be an unfortunate term, attentional inertia, because it could also be, as Martin, I think, was just suggesting, a reactivation of attentional parameters. Okay. So partitioning the residual cost, switch cost with ERP suggests that early processes are prolonged after preparation. How am I doing? A couple of other fragments of evidence for this idea of attentional inertia, that difficulty in reconfiguring the attentional parameters of task set contribute substantially, or can contribute substantially, to these mysterious residual costs. So Kai Longman in our lab used eye tracking to look at anticipatory eye movements from a central task queue to one of 3 locations, each location being consistently associated with a particular task through the whole experiment. Okay. And under at least some conditions, he found a switch of tasks led to a delay in shifting attention from the queue to the appropriate location, and also a tendency to fixate the previously relevant location. So I'm not saying the eyes stay on a particular location, they go back to the center every time, but the attentional parameter of where to go, as it were, is persisting from the previous task. Okay. And one reason I think this is interesting is that we tend to think, after Posner, a previous Bartlett lecturer told us, in fact, in a Bartlett lecture about preparation of attention, we tend to think that it's efficient, even though it may take a few hundred milliseconds to endogenously move spatial attention. But here's a case where it actually turns out not to be under some conditions, not all. You can also do experiments where you cue orientation of attention and nothing else. That is, the task set otherwise stays constant. All that's changing from trial to trial is the attentional parameter, where to or to what to orient your attention. Okay. So there is data of this kind for switching between dimensions, like shape and color. There's some nice evidence from this, from Ulrich Meyer's work and from visual search, where switching targets from a shape target to a color target when you have to detect a singleton you can prepare for that to some degree and reduce that switch cost, but you don't eliminate the residual cost. And I want to show you one other example that we've recently looked at, which is attending to voices in a multi-talker environment. So in this experiment, subjects heard a male and female speaker each saying a different digit name. Okay. The 2 voices appear to come from the same central location. And a visual cue 50, 800 or 1400 milliseconds before the speech onset directed attention to the male or female voice. And the task was simply to classify the digit in the cued voice as odd or even. That task stays the same. All that's changing from trial to trial, if anything does, is which voice you're attending to. And it switches on about 1 in 3 trials. And here is what I hope by now is a boringly familiar pattern. Okay? There's a huge switch cost of switching voices from trial to trial, and that switch cost reduces with preparation. And because this is recent data, confidence intervals have suddenly appeared on my slides, and these are all 95% confidence intervals. So there's a substantial reduction in switch cost, but there is also this very substantial residual cost. Okay? So preparatory tuning to the voice is possible here, but limited in efficacy. There's a large residual cost. Okay. And just one other point to mention, since I have a second. If you look at what happens after a voice switch, so these are now repeating on the same voice after it's switched, it takes quite a while to re-optimize the tuning to a voice. And it happens a bit quicker, or looks as if it does, for a familiar voice, that's actually the voice of the parents of these subjects, than it does for an unfamiliar voice, that is the voice of someone else's parents. Okay. Right, time to sum up. So I hope I've convinced you that once a task set has been acquired, task queuing experiments can be used to probe an important act of cognitive control, the re-enabling of a task set from procedural memory in the face of competition from other active task sets. I've argued that there's more to this competition than response conflict, and that task set competition is maintained by both transient carryover of a task set from trial to trial, transient task set inertia, and from associative reactivation of competing task parameters through longer-term associative learning. And I've illustrated using the RISC function to probe properties of task set reconfiguration. I've also described some recent evidence from partitioning of the ERP and task switching, and from other kinds of experiment, that endogenous tuning of several attentional parameters, though possible, is surprisingly limited in efficacy, and that this is part of the reason for residual switch costs in many experiments. So competition between attentional parameters is thus one way in which the task set competition is more than competition between SR mappings, but of course there may well be others. Now, I haven't offered you a grand model of task set control. I'm sorry about that, because I don't have one. Okay. What I have done is mention some models that view task set control as discrete memory retrieval, others that see it as top-down bias imposed on a continuum of relative task set activation. Whether one kind of account is right and the other wrong, or whether both descriptions can coexist like the wave-particle duality of subatomic physics, we don't know, or not yet. Some of the phenomena, notably the residual cost, remain perplexing. Why does doing a task once achieve what an endogenous preparation cannot achieve in terms of optimizing the readiness of a well-learned task set? But what I think we have achieved, since I asserted our more or less complete ignorance 2 decades ago, is a substantial body of robust empirical findings to constrain future computational models of task set control, and some theoretical ideas which they need to incorporate. And it remains to thank my collaborators again for their contributions, and to thank you for your attention.